Module 7, Risk Management and Laboratory Safety Protocols, ensuring safe and secure laboratory environments. The session is approved for 2 credits under CE by the AFAP. So there's a hierarchy of controls in risk mitigation. So what is the hierarchy of controls? It's a framework used to prioritize and implement risk mitigation strategies. It ensures the most effective methods are applied to reduce or eliminate hazards. There are 5 levels to the hierarchy. This hierarchy control provides a structured approach to achieving safer lab practices. This is the most to least effective. The first is elimination. This is the most effective, and this is to completely remove the hazard by either replacing, say replacing a hazardous chemical with a safer alternative. Some examples. A lab testing for heavy metals may eliminate the use of mercury thermometers, replacing them with digital or alcohol thermometers, therefore removing the hazard of mercury exposure entirely. So by eliminating the risk, by removing the potential risk, that is the most effective way to control risk. Next up is substitution, to replace the hazardous material or process with a less dangerous one. For example, in histology lab, xylene, a toxic solvent, is replaced with a less hazardous alternative, such as limonol-based cleaning agents, to reduce health risks to technicians. So this is done by trying to find safer alternatives. Now, oftentimes, a safer alternative substitution is not the same as elimination because you're not eliminating the hazard completely because you're still using toxins, solvents, you're still flammable. It still could have some toxic effects, but not nearly as toxic. It happens. Some chemicals are much more carcinogenic. They have more cancer-causing carcinogenic properties, and there can be better alternatives. But that does not completely eliminate the risk. Engineering controls. These isolate people from hazards, such as fume hoods, biosafety cabinets, or automated systems. Some examples. A molecular biology lab installs a biosafety cabinet to contain aerosols when working with infectious agents, preventing exposure to pathogens. This is creating an additional barrier to help prevent the exposure to infectious agents. Or automated liquid handling systems are used to minimize direct contact with hazardous reagents. Anytime you have a liquid handler, that reduces the exposure of the technician to the hazard, either the hazard solvents or the hazard sample. The matrix themselves could be considered bloodborne, and may have to consider bloodborne pathogens or solvents. The extraction process itself could be toxic. And having automated liquid handlers help reduce the effects, help reduce the risk for exposure. Administrative controls. These change work practices and policies, such as training programs or limiting exposure time. Some examples. A lab implements a policy requiring workers to handle volatile chemicals only in well-ventilated areas and schedules rotating shifts to limit individual exposure to the fumes. So trying to reduce exposure. It does not completely eliminate the risk, and there is some level of exposure, but it tries to reduce the amount of time and the amount of risk exposure time. Or mandatory safety training programs are introduced to ensure staff understand proper chemical handling and emergency procedures. If the chemicals cannot be avoided, then administrative controls can help ensure that the staff have proper training and proper opportunity to receive training to handle these chemicals and to help reduce the risk involved with them. The more they know, the more they understand, the better it is, and the more likely they are to not be exposed. And finally, personal protective equipment, or PPE. They use equipment to protect individuals, such as gloves, lab coats, or face shields. Some examples are lab personnel that are handling corrosive chemicals, wear chemical-resistant gloves, safety goggles, and a lab coat to prevent burns or injuries. And workers in microbiology lab wear N95 respirators when dealing with airborne pathogens to minimize inhalation risk. Another instance could be when handling dry ice, wearing protective gloves to reduce the chance of um, freezing your hands on an exposure. Some key considerations. Always aim for higher levels of control, elimination, substitution when possible. So always target the higher the level, the higher the high up the hierarchy, the better the risk mitigation is. And try to combine multiple controls for comprehensive risk mitigation. You can combine PPE, administrative controls, engineering controls, as well as substitution. Or sometimes if an item cannot be eliminated or substituted, it's good to implement engineering, administrative, and PPE. Rope those all together and you can get to the point, you can get close to the same level of substitution. And continuously evaluate and adapt controls to lab-specific needs. Digging into a little deeper, we spoke a little bit of biosafety cabinets or biosafety levels. Excuse me. Biosafety levels ensure appropriate containment and protection of biological elements. So what would BSLs be in terms of hierarchy of risk assessment? It is an engineering control. Biosafety levels are a set of safety protocols and containment measures designed to protect laboratory personnel, the environment, and surrounding community from exposure to infectious agents or biohazards. Sorry, biosafety levels are actually administrative controls with engineering controls tapered in. These controls, defined by the CDC and the NIH, are based on risk posed by the biological agents being handled. They range from BSL-1, the lowest, to BSL-4, the highest, with each level incorporating progressively stricter containment and procedural safeguards. So overview of BSL levels. BSL-1, for agents that pose minimal risk to personnel and the environment. These are not known to consistently cause disease in healthy adults, such as non-pathogenic E. coli. These require only basic lab safety protocols, minimal PPE, and no special containment is required. This is the lowest level of BSL. Next up is BSL-2. These are for agents with moderate risk to personnel and the environment. Examples of these are Salmonella and HIV. These include restricted areas to lab access, use of PPE, and biosafety cabinets for procedures generating aerosols and waste decontamination practices. This is oftentimes any laboratory testing with potential um, bloodborne pathogens or anything testing infectious disease would fall at minimum BSL-2. BSL-3. These are for agents with potential for aerosol transmission and severe disease. An example of this is Mycobacterium tuberculosis. These require controlled lab access, biosafety cabinets, and sealed environments. These are beginning to get a serious situation here. This is where any type of aerosols must be contained and contained within um, restricted access to laboratory space. And finally, BSL-4. This is the highest. This is for agents posing a high risk of life-threatening disease, such as the Ebola virus. These require full body positive pressure suits, specialized containment labs, and vigorous entry and exit protocols. This is reserved for the most severe. BSL-3 I did mention this, is oftentimes when you're cultivating live pathogens, oftentimes you're in a BSL-3. BSL-4 is when you have live pathogens and they are very high risk for life-threatening disease. Some key considerations. You need to match your lab practices, the biosafety levels of the agents being handled, and ensure proper training and understanding of containment measures by all personnel. All personnel should have the appropriate training to match the appropriate biosafety level. And conduct risk assessments to determine the appropriate BSL level for each activity. Every activity is going to have a different BSL, but often they're grouped together. You must maintain the minimum BSL for your laboratory, whatever it is, the activity you're taking. If you have a 1 BSL-3 activity, your laboratory must maintain a BSL-3 level of containment. I spoke on a biosafety cabinet. And the biosafety cabinet is a ventilated laboratory workspace designed to provide a sterile environment for handling biohazardous materials such as infectious agents or hazardous microorganisms. Biosafety cabinets are engineered to protect laboratory personnel, the environment, and the work materials by controlling airflow. They filter airborne contaminants through HEPA filters. So the containment, the biosafety cabinet protects the person, protects the environment, as well as protects your assay by controlling workflow. If your assay, you don't want to lose any aerosols, you don't want to create any contaminants within your assay, but you also don't want to contaminate yourself. So it provides multiple layers of protection. Some key functions of biosafety cabinet. They protect personnel. That's number one. They prevent exposure to infectious agents or harmful aerosols. But they also protect your product. They ensure that the work materials remain free from contamination during handling with the airflow. You have airflow, usually laminar flow, at the back of the hood and the front of the hood. What this does is it prevents um, crosswinds from moving and blowing aerosols both outside the hood as well as within the hood. And environmental protection. It minimizes the release of hazardous agents into the surrounding laboratory environment and therefore out into the world. Some types of biosafety cabinets. There are three classes. Class 1 protects personnel and the environment, but does not necessarily protect the sample. These do not have any flow. These just have typically shields. Oftentimes, these are just for PCR. These protect kind of the instrumentation um, from dust and particulates and protects the personnel, but does not create flow. It is suitable for working in low to moderate risk agents where sample sterility is not required. So this part is often BSL-1, and we have class 2. This, if you are in a BSL-2 environment, you need a class 2 biosafety cabinet or higher. This provides protection for personnel, the environment, and the sample. It is commonly used in clinical and research laboratories working with moderate risk biological materials. Subtypes include A1 and A2. They recirculate portion of the air after being filtered used with non-volatile toxic chemicals, or B1 and B2. These exhaust directly to the outside and they're used with volatile toxic chemicals. These are what they often call vented or non-vented. A1 is non-vented, B1 is vented. So it's going to suck out the air and push it out, whereas the A1 is only going to recircle it. So if you're dealing with a ton of solvents, especially flammable solvents or toxic solvents, then you're going to need the B1 or B2 to push the air out. Whereas if you're dealing with less toxic solvents or no solvents, then you want an A1 or A2 with recirculation will be sufficient. Most infectious laboratories are going to have a class 2 biosafety cabinet to maintain their BSL-2 level. But Class 3, this is a gas-tight enclosed cabinet that provides maximum protection for personnel and the environment. This is required for handling highly hazardous agents, such as BSL-4 agents like Ebola. Oftentimes, BSL-3 or higher is going to require a Class 3. A BSL-3 can get away with a Class 2 sometimes, but sometimes they require Class 3. BSL-4 will always require Class 3. The key features. They have HEPA filters. These capture 99.97% of particles 0.3 microns or larger. They have a laminar airflow. This ensures a unidirectional flow of air to maintain stability or sterility. And a front access opening. This allows for manipulation of materials while minimizing risk. And alarms and safety mechanisms. These alarms alert users if airflow is compromised. Most times, these systems come with airflow alarms for the front, for the back, the door. The door is raised too high, then potentially exposing the technician to the hazards. Therefore, it'll warn, alerts will go off, and therefore the technician will know what to do next. Biosafety cabinets are a critical part of a laboratory infrastructure, ensuring compliance with biosafety regulations and maintaining a safe working environment.